quantum mechanical model. As you'll see from the sort of disclaimer at the end of the title, I don't actually do much tribological simulation myself, so I'm hoping I'm presenting methods that will be of use to this community, but I'll be very interested to hear whether that's the case or not in the discussion that comes afterwards. But first, a little bit of sort of motivation and an explanation of my background and where I've come from in terms of applying these sort of atomistic modeling approaches. I've almost entirely worked on what I would class as chemomechanical problems. So problems that combine chemistry, breaking bonds, and stress and mechanics. And so the most prominent example is probably fracture. So the individual bonds at the tip of propagating crack have to be broken, and that's chemistry, but it's driven forward inexorably by the concentration of the stress field, which was imposed by boundary conditions that are placed very far away. Friction involves very similar processes, altogether more complex typically, but there are of course relations between friction and fracture that can be exploited. So initially, a lot of the applications work that I did was in fairly simple brittle covalent materials, things like silicon, carbon, silicon carbide. We'll hear a bit more about them later on in today's talk as well. I also worked for a while on oxides, so silica glasses, etc. And more recently, since expanding a bit more into plasticity, I've been working more on metals and trying to understand things like how to prepare improved tungsten shields for nuclear fusion, or how to control embrittlement processes in steels, etc. So these problems are all linked by needing to, in principle, provide a quantum mechanical description of chemistry, but meeting the challenge of needing to model large systems and large nanoscales and long timescales. So I'll return to a picture that we've seen at least once or twice already. I think Michael had a version of this earlier on, which shows the sort of trade-offs associated with the quality with which one describes a system and the accessible length and timescale. So if we want to model the effects of atoms and understand things like fracture and friction, we at least need to include the atoms explicitly. So that means at least down at the molecular dynamics level or below. But as I've indicated here, often that's not sufficiently accurate to be able to make quantitative, experimentally verifiable predictions. For many materials, DFT is sufficiently accurate to make predictions. Not all materials, of course, it depends a little bit, but the systems that are directly accessible are somewhat limited. This picture is pretty old, so probably we could go a factor of 10 up and consider 1,000 atoms or so, but that still doesn't get you very far when modeling even individual asperity contact or fracture. So what I've done over the years is spend quite a bit of time coupling different length scales together. So you get the best of both worlds. You have a quantum mechanical description of places where bond breaking is actually happening, embedded within a much larger, simpler description that allows you to have appropriate elastic boundary conditions. So to give a quick example of how that works for fracture, we can consider 10 to the 5 or 10 to the 6 atoms with clamped boundaries. So the boundary conditions are imposed far away from the tip of a propagating crack, and therefore we have a constant flow of energy to the crack and stable crack propagation. To describe bond breaking, we use a couple of hundred atoms at density functional theory level, and we can get a nice description of the mirror smooth fracture surface expected, in this case, cleavage of silicon on the 111 cleavage plane. The downside, however, is that we're limited to timescales that can be accessed by density functional theory, and hence the motivation to develop accelerated techniques using approaches like machine learning that embody the quantum mechanical processes that we've seen here, but in a more computationally efficient manner. Worth mentioning before I move on, however, that a nice approach of anything that involves quantum mechanics directly is its intrinsic transferability. So you can put as much, I'll just play this maybe once more, as much complexity, chemical complexity, etc., as you like in here, without having to reparameterize any models, assuming it's within the domain of applicability of the tool that you're using, density functional theory in this case. So just one recent example, one ongoing example of this approach. This is fracture in diamond. So we've got a piece of diamond here in the top specimen. This is pure diamond. We're seeing cleavage, individual bond breaking in a 111 cleavage plane. And the associated experiment sees a very close to smooth fracture surface. Whereas if we place isolated nitrogen impurities ahead of the path of the crack, we occasionally see interactions between the propagating crack and the nitrogen impurity. Being diamond, it's happy to form sp2 hybridized layers or sheets, so graphene-like sheets, and these lead in turn to a step up in the propagation direction, which is manifested in experimentally observable micron scale features. So this is related to previous observations that I've made in silicon and where we saw interaction between cracks and boron. A little bit more complicated here because of diamond's willingness to form much more sp2 than silicon, which is invariably preferring tetrahedral sp3 bond angles. One further example that's perhaps interesting for this community, so a more complex system, we're looking at here a nanotube-polymer composite, so pulling a nanotube out of a matrix of polymers. In this case, we're using a simplified description of the quantum mechanics so that we can model many contact points simultaneously. So density functional type binding is used for the quantum mechanics, and sort of classical interatomic potential that's been well calibrated for the relevant organic polymer molecules. The detection of which regions need to be treated with high precision is a bit more sophisticated in this recent example than in what I showed you earlier on. So all atoms where the classical energy exceeds some threshold are flagged for quantum mechanical treatment, and that means that all of the contact sites between the polymers and the nanotube will be automatically flagged as needing a higher level of theory, and we can sort of validate that in a straightforward fashion by looking at something like a stress strain curve. So as we pull on this nanotube, the force that we need to apply in order to pull it out, to extract it from the composite. If we use the classical model alone in green, we significantly overestimate the failure strain, whereas using either a fully quantum mechanical calculation, so expensive one-off reference calculation, or the hybrid approach, the quantum mechanics, molecular mechanics approach, leads to the same pull-out force and failure at the same strain. So this is a useful technique where it can be applied, but we are limited in terms of the timescales of the dynamical processes that we're modeling to what you can get to with the quantum mechanical method of interest. One way to lift that timescale restriction is not to look at the dynamics explicitly, but to look at energy barriers for activated events. One challenge in doing this was the way that the forces are combined. We mix together quantum mechanical forces on atoms, which we need to treat at a high level, with classical forces elsewhere. That gives us overall accurate forces and hence good trajectories, but there's no total energy, no Hamiltonian associated with this system. We can, however, use something akin to thermodynamic integration to integrate forces times displacements and compute the virtual work associated with a given process. And this works well to measure energy barriers for simple processes. So we first validate on something where we can do the DFT calculation directly, that's vacancy diffusion. And then we go and try it out on something rather more complicated. This is a dislocation motion barrier, so the Pyrrhus barrier for an edge dislocation in molybdenum. Here, the best available interatomic potential massively overestimates the energy barrier in comparison to the quantum mechanics-based scheme, which can be nicely converged by making the quantum calculation better isolated from its environment. So cranking up what we call the buffer, the region that surrounds the core of the quantum region. So for sufficient computational resources, we can converge to high precision and make useful predictions which are transferable. But once you've done quite a few of these calculations, you realize that history is rather repeating itself. Each bond breaking is rather like the one before. It shouldn't be necessary to perform expensive calculations each time. And this idea actually goes back nearly 20 years now to embody what we see happening again and again in a simpler representation. Originally in the Learn on the Fly scheme, this was through the parameterization of a simple fixed model. So we have some underlying model which we augment locally in space and time, and when we extrapolate with fixed parameters and then go back and reinterpolate the dynamics between 2 points at which the fit is assumed to be good. It probably should retrospectively have been called fitting on the fly, not learning on the fly, because nothing was truly learned, nothing was remembered, and so it's appealing to try to go beyond that, and that's where the idea of Gaussian process regression, something we heard about earlier on from Louise, is quite appealing here as well. So what we're trying to do when we fit a Gaussian process is figure out what the most likely function is, given some data and given some prior assumptions about what the model should behave like. The main way in which prior assumptions go in when thinking about applying Gaussian processes to fitting interatomic potentials is through a covariance kernel. So what that is really doing is telling us how smooth a function is. It tells us the correlation between the value of the function here and somewhere else. And a length scale enters effectively provides a prior for how smooth the function should be. So let me just show you roughly how that works. We start with a prior distribution. We condition it or narrow it on training data. We come up with a posterior envelope. So a prediction of the mean function, most likely function, but also we can draw samples from the posterior. That's what the orange lines are here. So these are all different functions that are compatible with the data that we've provided. And we're going around again. You can see as more and more data is provided, we approach the truth, which in this case was a very simple sine wave, but depending on the complexity of the model, could be much more demanding. The nice thing about the approach is that it's analytically tractable. So one can actually just do some linear algebra and write down both the mean, the prediction, and the expectation, and also the variance, so the predicted error, as a function of evaluating this kernel between training data and also places where you'd like to make predictions. And what you end up with here is some weights which have to be applied to a vector of kernel evaluations comparing each of your training points with what way you'd like to make predictions. So this can be done once and fixed, and then to make predictions, it's just a dot product, essentially, on top of the cost of evaluating whatever your kernel is. So the first application of this that I was involved in was to try to build on the learn on the fly idea that I introduced and make it truly learning. And what we were looking at doing was either predicting, where possible, using Bayesian inference, what the forces on atoms should be in comparison to observations that have been made previously, or where necessary, where those predictions would be insufficiently accurate, we could go ahead and do some active learning, so compute on the fly with DFT and add to a growing database. And this was a few years ago now, five years or so ago. A number of people have built on it recently, and this paper was particularly nice innovation. What we found when we did it was because of the simplified way in which we represent the environment and the way in which forces depend on the environment, we essentially got to a point in a complex situation, let's say 1,000 Kelvin piece of silicon, where after a picosecond or so, we settled down at needing to do one quantum mechanical calculation every 30 time steps. So a speed up compared to the simple fitting, where we got about a factor of 10 speed up, but really not sufficient to fully describe the complexity of the material. And so this sort of feeds into the parallel story of Gaussian approximation potentials, where the approach instead is to build a potential. So this is the functional form that's being used here. There's some simple two-body interaction just to stop atoms from misbehaving when they get too close to one another, but most of it takes the same form as the Gaussian process that I showed you just now. A detail which is quite important, so this sum doesn't run over the whole database, but is over a much restricted set of what we call sparse points, so representative elements within the data set. So in this silicon application from a few years ago, we had about 2,500 TFT evaluations containing a total of 170,000 atomic environments. We picked out 9,000 of them to represent it and essentially to use as a basis on which to make predictions of the rest. And so if you want to fit such a model, what you have to do is form a kernel matrix between all of those representatives. So that's a 9,000 by 9,000 matrix, and then some tall, thin matrices which compare those representatives to everything else. You get to specify how much weight you'd like to put on each observation, and that can be interpreted in a Bayesian fashion in terms of the assumed error in the input training data. So you have a nice way to think about the weights that you're putting on the data. And that data can comprise observations from DFT of energy, forces, and stresses as well. So direct observations. We can think about the accuracy in terms of how well we predict forces, for example, and you can see it's a significant improvement over previous interatomic potentials. But I think much more important is to think instead about accuracy in terms of properties. And that's something I want to emphasize in the last part of the talk, last 10 minutes or so of the talk. So this is a picture that shows how well this particular potential does on a number of different properties. So we've got some bulk properties here, bulk modulus, elastic properties. Surface energy is also important for tribological applications, and point defects. Again, very relevant when studying complex mechanical processes. The figure, the parts shown over on the left-hand side here were things that were in some way represented in the training set. So it can be thought of as verification in the sort of software engineering sense of what we put in, and making sure that what we put in comes out again to high accuracy. Whereas what's shown on the right is a more challenging test, or more of a validation, a scientific validation test, in that we weren't representing these grain boundaries or these stacking faults, and still the predictions are within sort of 10–15% of the DFT prediction, unlike many previous interatomic potentials and even some more expensive methods like type binding in many cases. Just to give a couple of more specific examples that I hope are interesting and relevant for tribological and tribochemical applications. This is amorphous silicon, first of all. So the liquid radial density function and angular distribution function are well described, as is the temperature-dependent diffusivity. So limited experimental and density functional theory data. One can obviously afford to do rather more calculations with the potential than you could with either of those other approaches, but they are broadly consistent. We shouldn't expect the machine learning model to do any better than the data on which it's trained, so it can't fill in anything that's missing in the density functional theory, and that might explain discrepancies with the experiment. The amorphous is also very well described, amorphous silicon. So when we quench as slowly as one can afford to do with what is still quite an expensive potential, we get a good agreement with experiment. No direct comparison to DFT in this case because the quench rate is too slow to do that directly with DFT. And then one can start to map out the phase diagram and look at the stability of various phases. Again, we shouldn't expect the model to do any better than the data that it's trained on. So what we're able to do is effectively map out the true DFT phase diagram that we can't afford to access with DFT, but with a surrogate model, with an effective model that's doing almost as good a job as DFT, we can map out that phase diagram, make predictions about where the liquid-solid transition line would be, and it agrees well with the limited observations that can be done with DFT, but it doesn't capture the full complexity of the high-pressure phases. So we say that this potential is pretty good for everything at sort of reasonable temperatures and pressures, experimentally accessible typically. A more challenging test is what we call a random structure. So throwing atoms into a box, randomizing their initial positions and randomizing the shape of the box as well, and then quenching and relaxing down and seeing where you end up. And this is a very challenging test of interatomic potentials because it's checking whether the accessible phase space volume is reasonable, and whether you can get to comparable quality of the potential energy landscape overall to what you get with density functional theory. So what we see here in black is what we get when we do these structure searches with DFT. The gap potential is shown in red, and it's the one that's matching up most closely. So down here is just the convex hull of all the points that are shown up here. This is the density of states that comes from integrating along this axis essentially. So we see a very good agreement. And many potentials have lots of spurious local minimum that trap them at high energies. And it's quite nice that we don't see that so much with the potential. I often get asked whether the approach is applicable to more complex systems, and I'm pleased to be able to show some early results on extending to a binary system, so silicon carbide, which I know is interesting from a tribological perspective. So this is a PhD project that Harry Tunstall is working with me and Gabriela Soso here at Warwick. And this model has been trained on DFT data, including liquid quenches, and then we're doing a lot of iterative training. So we build a model and then we use that model to go off and do some dynamics, interrogate it and feed that back in and go around. And at this stage, after a couple of years or so of Harry's PhD, we've got a very good prediction of the liquid, so in good agreement with density functional theory performed with equivalent settings, essentially, so we can make a direct comparison. And if we look also at the amorphous, initially comparing the blue gap curve with DFT quenched at the same rate. So what I'm showing first of all is a very fast quench that we can afford to do directly with DFT, so that we can see whether the potential is matching up with the training data that it should be expected to. And then the advantage of having a surrogate model, a machine learning model, so we can actually go and run it much more slowly and see where we can then improve the agreement of experiment. So that's something we've done very recently. We're seeing some quite encouraging signs that this first peak here is brought right down when we quench at a much lower rate, and admittedly still a rather fast rate compared to any experiment, but the first peak is coming down. The second peak is perhaps going up more than we would like. We can dig into it and try and understand what's happening. Incidentally, the way that we were able to produce a reasonably good potential here was by using metadynamics to drive the sampling. So once we'd built a reasonable potential, we then constrained the coordination number for the silicons and carbons and pushed it in a particular direction in the amorphous structural space in order to improve the sampling and add new training configurations. And that's what we needed to do to start to get closer to the experimental radial distribution function. I'd say that we're doing at least as well as existing potentials in the literature. So this is a paper of Lars's from a few years ago. You can see that there's significant overestimation of that first peak by other widely used potentials. And so it's quite encouraging that we're able to bring that down. And the structure out here is also in reasonably good agreement with the experiment. Okay, just a couple of final thoughts on other challenges of these approaches. So people often say, I can't use these machine learning potentials, they're far too slow. I need something which is more comparable in cost to something like embedded atom method or simpler potentials. So there's been a recent push in that direction to simplify the construction of these models and see whether comparable accuracy can be achieved. One way to do that is to use a fixed basis function and to, instead of using a kernel-based model, just have a series of coefficients here which are directly optimized in order to match DFT reference data. So you can do that in a linear fashion, or you can go one step further and first fit a linear model as described here, and then use a second term, a quadratic term, which is effectively building on the accuracy that's frozen in the linear model and adding a small correction, but without risking too much wild extrapolation, because it's constrained to be a smaller overall contribution. When we use this approach, we are able to construct accurate models for iron and tungsten that do a good job of describing fairly complex dislocation barriers. So we've got a DFT curve in black here. The linear and quadratic models are matching it quite closely for both iron and tungsten, whereas earlier gaps are not doing so well here, possibly because of the quality of the DFT data they're trained on. That's always the main determinant of the outcome. But possibly also it's nice that these models have less risk of overfitting because they're intrinsically simpler models. Okay, I think I need to make sure I get through the last point or two and have a bit of time for discussion. So I really wanted to just finish by saying that if you're trying to model very complex and very long timescales, it's really important for us to start thinking more seriously about how to quantify the uncertainty in the predictions that we're making. And I think that as we move to 3 dimensions, to complex chemistry, to complex impurities or multiple active processes, this becomes more and more urgent and important. And that's a key philosophy behind the center that I lead at Warwick, the Center for Predictive Modeling. I'm trying to add uncertainty predictions at all steps and scales in this hierarchy. So right down at the bottom, electronic structure methods are not accurate. They are precise. You can converge them very precisely, but they don't agree with experiment because there's an uncontrolled approximation in the exchange correlation function. And one can start to think about how to quantify that. Moving up to the interatomic potential level, I'll just show one example of that in a minute. We can start to think about how to quantify uncertainties arising from our lack of knowledge about the potential, both through parameters and also through the functional form. So I'll just show one example of that comes from this silicon gap work from a few years ago. So as I showed you, the Gaussian process framework gives you an analytical solution for the predictive variance, but we're not actually following that recipe completely, just for efficiency reasons. So we're only using the sparse points here. We're not using every point in the database, and we're applying some simplified regularization that's a sort of a user parameter. But within those limits, it starts to be useful. So we can make predictions. Here we see a vacancy migrating backwards and forwards. So a very simple process compared to what many of you are interested in modeling. But it's useful to start to be able to see where one can trust this potential and where we have to be a bit more cautious. And essentially, in this case, the minima are well described. They were represented in the training set, whereas the saddle point wasn't. And you could go back at this point and sample from the barrier calculation and put explicit description of the saddle point in, and then you would expect to see that red come back a bit more blue, essentially. Okay, I wanted to run through a few kind of messages, implications. So I've shown you that multiscale techniques can help to provide localized injection of quantum mechanics if you can do that in a way that is compatible with your simulation, but they're still going to be much slower in classical force fields, even when we augment them with machine learning. The current generation of machine learning potentials, I would say, are already useful and predictive for things like liquid and amorphous materials, reasonably simple materials. And they can be further accelerated through reductions in the complexity of the basis sets. I think it's really important when considering whether to use such a model to think about the accuracy of properties, not just training test splits on energies and forces. So we really need to be thinking a bit more about what we're trying to predict with these models and how well we can trust it. And closely related to that, if we want to improve transferability, then we need to be more serious about propagating uncertainty through models from the limited training data through to the predictions that we'd like to make. And that would then allow us to use these accurate models that we now have together with this active learning idea that I presented earlier on to automatically incorporate new training data as required. And then finally, linking that back up with what I talked about at the very beginning of the presentation, there are a lot of opportunities to start to quantify uncertainties as we move up through the scales as well, and using ideas like relative entropy to measure the information that you lose when you go from a complex model to a simpler one and associate an uncertainty with that. Okay, I'll finish then by thanking everybody working with me at Warwick and elsewhere, and also the funding agencies and computing resources. And I look forward to discussing.